Hi, this is Dr. Viv. I would like to teach you a method which is rarely taught anymore, known as reverse induction. It'll enable you to find general formulas for series involving products of powers of natural numbers, such as the series indicated here, which is the sum of n times n minus 1, which is 1 times 2 plus 2 times 3 plus 3 times 4, all the way to n times n plus 1. Now, to get some sort of an idea how this might work, let's recall something very basic, and that is the sum of n numbers. Suppose I had 1 plus 2 plus 3 all the way up to n. What would that be? There are many ways to prove what the general sum of that of the first n integers are. The cutest proof I know by far is the one by Gauss. It is said that Gauss was an unruly child, so the teacher assigned him a problem of calculating the first 100 or the first 50 integers summed together. What Gauss did was incredibly clever. He wrote the same sequence in reverse order. So n plus n minus 1 plus n minus 2 all the way down to 3 plus 2 plus 1, and let's call the sum s sub n. Then that sum is also s sub n, and then he simply added them together. When you add that, you're going to get 2 sub s sub n. Now if you add directly below, that's going to be n plus 1, and then 2 plus n plus 1 is n minus 1 is also n plus 1. And each time you add, you'll notice that n minus 2 plus 3 is also n plus 1. So you're getting the same thing n times. And if you have the same term n times, the answer is n times n plus 1. So the sum Sn is n times n plus 1 over 2. Incredibly beautiful proof, and Gauss was able to finish this proof in a matter of minutes, and that was the first indication to the world that here was a great genius. In fact, Gauss is now regarded as one of the greatest mathematicians that ever lived, not for this, but for many other later things he did. So what I want to get from this is a lesson. If I have something like this, then I'm getting a quadratic expression. So if you write this out, I get n squared over 2 plus n over 2. So maybe there's a way for me to do this. Let's say, because I'm not as smart as Gauss, maybe there's a slightly easy way to do this thing. So what if we wanted to find the sum of n integers but did not know how to do this trick? Then what you would do is assume that Sn would be sum a times n squared plus b times n. Then what you would imagine doing is add one more term. So if you add the n plus 1th term to the sequence, the answer is going to be a times n plus 1 squared plus b times n plus 1. In fact, this is the inductive hypothesis. So this is the place where you use the inductive hypothesis. And now what you would do is subtract the two. So if I do Sn plus 1 minus Sn, now if I look at the actual sequence, Sn plus 1 has got all terms 1 plus 2 plus 3 all the way up to n plus 1, and maybe one more term here, n plus 1, and Sn has got terms going up to n. So the difference between these two is just going to be n plus 1. So that's straightforward difference coming from just looking at the actual series. Now we're going to look at the difference from this assumed formula. So from the assumed formula, the difference is going to be a times n plus 1 squared minus an squared plus b times n plus 1 minus bn. So let's try to simplify that. N plus 1 squared is n squared plus 2n plus 1, and then I have a minus n squared plus b times n plus 1, and then I have a minus n. So you notice that the biggest coefficients of the biggest terms cancel out. So I'm going to equate the two ways of writing Sn plus 1 minus Sn. So that's therefore n minus 1 must be equal to whatever I have here, the second way of writing it. And so that's going to be a times 2n plus 1 plus b. Now here I can gather together the coefficients of each power of n. So I get 2a times n plus a plus b. And then I can compare both sides. If I compare both sides, I immediately get the result that a equals 1/2, because 2a must equal 1. And once a is 1/2, a plus b must equal -1. So if a plus b equals sorry, I don't know why I wrote -1 here. It's n plus 1. A plus b must equal 1, which means that b is also equal to 1/2. And indeed, we get this formula back because 1/2 and 1/2 are precisely the coefficients of n squared and n. So this method actually works, and this is a sort of method which I can do, and I'm no Gauss. So maybe we can apply the same method to find out the general formula for that. So let's try that. What we're going to do now is we're going to assume, we're going to call this, I have no better terminology than S sub n. So I'm going to just call S sub n, which is the sum from n equals 1 up to n of n times n plus 1. Now if I have a linear set of terms, I'm going to get a quadratic answer. So if I have a quadratic expression to start with, I must get a cubic answer. So I'm going to assume that this, which is equal to 1 times 2 plus 2 times 3 plus 3 times 4 all the way to n times n plus 1, can in fact be written as an cubed plus bn squared plus cn plus d. So you can see that there's more coefficients because we are assuming a cubic form. Now strictly speaking, I should have written an squared plus bn plus c, but because I already knew the answer was only going to have an n squared and n, I did not bother doing that. But in general, we don't know this. So we have to add, we keep going down until we get n to the power 0. So if you want to be super precise, that's what's going on here. So now we'll apply the same trick, s of n plus 1 minus s of n. Well, if you do the first way, writing out the n plus 1 terms and subtracting the n term, you're only going to end up with the n plus 1th term. So what is the n plus 1th term? The n plus 1th term is going to be n plus 1 times n plus 2. Basically, it's the last term. Instead of n, you make it n plus 1. Now this is also equal to the second way of doing things, which is using the formula that you have assumed and subtracting for n and n plus 1. So that's going to be a times n plus 1 cubed minus n cubed plus b times n plus 1 squared minus n squared plus c times n plus 1 minus n plus d minus d. So you can't get any information about d. We'll learn how to fix d using what's called the base case in an inductive proof. Right now it's just down to business. N plus 1 and times n plus 2 can be simplified. So I get n squared plus 3n plus 2. Now what about n plus 1 cubed? Well, the general formula for that is n cubed plus 3n squared plus 3n plus 1 minus n cubed, just as in that reproductive proof for Gauss's formula. All the highest terms will cancel out, and then what you're going to get next is going to be what you saw in the earlier types of problems. So I get b times n squared plus 2n plus 1 minus n squared plus c times, well, n plus 1 minus n, I just get 1. Okay, now let's look gather together all the coefficients, I get a here, and I get just a with the n squared term, 3 times a times n squared, and then I'm going to start getting one more for each lower coefficient. So I'm going to get 3a plus 2b for the n to the power 1, and then for n to the power 0, or just constant, I'm going to get all three. So that's going to be a plus b plus c. In all these proofs, the last term is always going to be a plus b plus c, or if you have formulas involving cubes, you're going to have a plus b plus c plus d. Okay? So now we just compare the coefficients. That's really easily done. 3a must equal 1, which tells me that a must be equal to 1/3. Let's box that so we can find it. Once you have a equals 1/3, you can proceed to the next equation. I'm going to get 3a plus 2b must equal 3, because that's the coefficient of the n to the power 1 term. So I'm going to get 3 equals 3a plus 2b. But since a is already 1/3, this becomes equal to 1, because 1/3 times 3 is just 1 plus 2b. Now I can subtract 1 from both sides. So this equation is 3 equals 1 plus 2b. That can be written as 2 equals 2b, which means that b equals 1. Last thing is to do the coefficient of the constant term. So that gives me a plus b plus c equals 1. Well, since I already know a is 1/3, this is equivalent to 1/3 plus 1. I'm sorry, I did not do the right thing right. A plus b plus c must equal 2, because I'm looking at the coefficients. So that gets 1/3 plus 1 plus c equals 2. Well, 1/3 plus 1 is 4/3, or I'm actually feeling lazy. So I'll just subtract 1 from both sides. So I'm getting 1/3 plus c equals 1, and now it's much easier to do. So I get c equals 2/3. In this manner, I've determined a, b, and c. But what about d? So to determine d, we can consider what's known as a base case. In every inductive proof, you have to verify base cases. So that is, show if you already have a formula and you want to show it's true by induction, you usually have to invoke a base case for low values of n. That's exactly what we're going to do now. So because this is a reverse induction, this is the last step of the induction, of the reverse induction. So consider the base case n equals 1. That's always the best base case to use. If n is equal to 1, then S1 is simply 1 times 2, or that's equal to 2. Our formula should reproduce that base case result. Our formula is that. So in our formula, S1 is going to be a times 1 cubed plus b times 1 squared plus c times 1 plus d. All that must equal 2. But I already know that a plus b plus c is equal to 2. If a plus b plus c equal to 2 and a plus b plus c plus d equal to 2, that can only have one implication, and that is d is 0. So the d term never comes. So our general formula, we have found our general formula. You don't have to be as smart as Gauss to do this. Sn is equal to an cubed plus bn squared plus cn. There is no d term. And now let's put all the values. I get 1/3 n cubed plus n squared plus 2/3 n. Amazing. We have found the sum of the products of successive integers, successive two integers. And this is equal to 1 times 2 plus 2 times 3 all the way to n times n plus 1. You can actually use this. You can have a lot of fun if you're really bored or if the power is out. You can try doing a few problems. I'm going to suggest a few problems. So let's do the lowest hanging fruit first. You can try n squared. Okay, so that's the one thing you can try. Then you can try everything in the cube family. N cubed. In the cube family, you're going to have things like n squared times n plus 1. You're also going to have things like n plus 1 times n squared. N plus 1 squared times n, sorry. What else? Oh yeah, how about this? N times n plus 1 plus times n plus 2. So you can find formulas for all of these. All of these will involve, assuming your formula to be of the type ab to the 4 plus, a n to the 4 plus bn cubed plus cn squared plus dn plus e, which will always turn out to be 0 using the base case. So try that on your own and have fun.